So in this lesson we will look at first the mold filling. So we looked at geometry in the last lesson, so now we will look at how the metal fills the mold cavity. So we will look at some of the basic properties of metal, okay, and we will see how metals behave. How do you, am I doing right? So we will look at the flow part of it, and we will introduce concepts like what is velocity, what is the pressure, what are the losses in during flow, turbulence, fluidity, all these terms which are used in the industry, but we will go deeper into meanings of those terms and we will see how they really affect our castings. This is going to be first part of it, and then the next lesson we are looking at the solidification of the metal and how the metal solidifies, temperatures, gradients, cooling rates, how they affect the defects formation, how they look at the properties and all those things we will look in the next session. Okay. So as said, you imagine, okay. Now metal flow in a mold has all the natural phenomena that you come across in sceneries like this. So you see a waterfall and metal fall in a sprue, okay, that happens really, and that side picture is a simulation of how the metal falls through the sprue, okay. Then you have these streams turning around and creating a vortex in nature. You do see vortex also as a sprue metal enters the sprue and starts twirling. You start seeing those vortex, and vortices, remember, they are dangerous because they suck clay and air and even small stones in nature. In this case it will suck in air and slag and things like that, sand particles and all that. The third is splashing against the walls, okay, and you should imagine a seashore and see how the water hits against the rocks in a sea. Similar kind of a thing happens when metal smashes against the walls of a mold, okay. And the last phenomenon is streams separate and then streams come together and then they meet. So splitting and merging of streams happens in nature, happens in a mold also, except that in nature you are able to see all those things. Inside the mold we don't know what is going on, we can only imagine what is going on, because both sand mold and metal mold are not transparent. So as it happens, the mold filling is the shortest even in the entire life cycle of a casting. You take days to prepare the tooling and then hours to prepare the molds, and eventually you are going to machine for several hours, and finally life cycle of a part maybe 10 years. In the entire life of a casting, the shortest event but the most important event is the filling of the mold cavity. It's a transient phenomenon. Transient word is used in mechanical engineering to denote events where there is a continuous change in several parameters, okay. Here this pressure is changing, velocity is changing, temperatures are changing, okay. What else is happening? We just looked at metal is falling, vortex is forming, splashing is happening, turbulence takes place, mold can get eroded, air can get aspired and mixed with the melt, okay. Then streams are separating and rejoining. The air and the gases in the mold are resisting the flow of metal progressing in the mold cavity. Then the advancing front is oxidizing, okay, and then you have solidification starts. Even before the mold fills completely, solidification starts, okay, and the properties are changing all the time. It's so complicated that, as I mentioned earlier, we say metal casting is rocket science for rocket scientists. We say something is difficult, we say it's rocket science. This is rocket science for rocket scientists. People have given up trying to do research in metal casting because it's simply too difficult to understand, okay. Your research is happening in every field but except metal casting, at least fundamental understanding of that, okay. A few people are working, as I mentioned in the morning, some gurus, but it's a very handful. In India it's very difficult to find people who want to continue research in this area. Now I mentioned to you about the metal itself. So if you just look at the 3 or 4 common metals, and through the course we will talk about aluminum, maybe iron and steel, at least aluminum and iron and aluminum and steel as 2 different range of metals handled in metal casting. If you look at that, look at density, that is room temperature, density at the liquidus, surface tension and dynamic viscosity is there. I have not put the value of kinematic viscosity, okay. Let me just give you a hint of that. If you look at kinematic viscosity of water, which is 1 centistoke, in fact that's a definition of viscosity from water at room temperature, okay. Diesel oil 10 centistokes, honey about 70 centistokes, glycerin around 1000-1200, coal tar 10,000. On this scale, where do you think is the kinematic viscosity of molten metal? and I want some guesses here. Between diesel and honey. Okay. Any more? Which is next close to coal tar. Okay. Between honey and glycerin. Okay. But you are just waiting for what is left out. Okay. How do you calculate kinematic viscosity? If anyone knows the equation of that, dynamic viscosity divided by density. That is kinematic viscosity. Surprise, surprise. It is even less, viscous than water. Or molten metal at a pouring temperature is of the same order as water. So it's not too difficult to imagine molten metal flowing in a mold. You just imagine water flowing in a mold. Okay, and that's the beauty of analysis like this. Now let's start looking at pressure. Okay, we know pressure is rho GH. That is high school formula. Everyone should be remembering that. We also know the atmospheric pressure at the Earth's surface is equal to 100 kilopascals, right? And rho GH is in Pascal. If rho is density is in meter per kg per meter cube, G is, you can say 9.8 or just make it as 10 meter per second square is fine. Head is in meters. Okay. Now, what do you think is the pressure exerted by a column of only 20 centimeter of, let us say, steel? You think it's going to be more than atmospheric pressure or less than atmospheric pressure, or what fraction of that? Okay, it takes time to calculate, so let me put the answer. It's about 5 to 15, 5 for steel, 5 for aluminum and 15 for steel kilopascals. Compared to atmospheric pressure, which is 100, this is just a fraction of that. But remember, the atmospheric pressure acts on the metal also. So the pressure at the bottom of the mold is going to be 100 plus, let us say 15 for steel. Of course, atmospheric pressure acts on the top also. So you're looking at only differential pressure, which is what is going to drive the metal into the mold cavity. So we have to finally calculate using this 15 kilopascal to convert this pressure into finally velocity, which is what leads into mold cavity. Now, just as comparison, in a pressure die casting, the pressures can be as high as 50 to 150 megapascals. So first of all, qualitative difference between sand casting and pressure die casting is pressure die casting pressures are several orders of magnitude, 100,000 times higher, and that creates a different kinds of problems. So that is about pressure. Now from pressure we can convert into velocity, because the potential energy of a pressure converts into kinetic energy of the flow, and if you have the basic mgh is equal to half mv square, you get velocity basic equation, which is root over 2gh. Okay. Now again take the same example of 20 centimeter mold height, and the velocity at the bottom of that will be approximately 2 meter per second. And typical velocities in most molds are of this order, a few meter per second, okay, 1, 2, 3, something like that. Now again compared to pressure die casting, their velocities can be as high as 20 to 50 meter per second. Again talking about 10 to 50 times higher velocities in pressure die casting than sand casting. And velocity doesn't increase directly by height. So if you plot that equation into a graph form, you see that as the head is increasing, velocity is increasing, but not that much. It's not proportional, it slows down. This is fine. Now we talk about flow through a closed channel like a sprue or a runner or a gate and things like that. So when metal is flowing through closed channel, we have one equation comes into picture is mass balance. I mean, you cannot recreate additional mass. So what goes in is what comes out. So A1 V1 is equal to A2 V2 is the fundamental equation. Now let's look at 3 examples here. If the pipe area is constant, cross section area is constant, A1 is equal to A2, then V2 will be equal to V1 from this equation, clean. If the pipe area reduces, velocity should increase, and so V2 will become more than V1. Now the third case is where we have a problem. If the area increases, A2 is more than A1, we are supposed to have V2 less than V1. But I am saying there is a question mark there. Does it really happen? Why it won't happen? Any reason? Why? Fundamental laws of physics should be followed, right? It doesn't happen because the flow starts separating from the mold walls. Flow doesn't follow the walls, it will just come out of the wall. Okay? And so your V2 may not be less than V1, it may be equal to V1 or less than V1, it could be anything. On top of that, we are creating an additional problem that when flow separates, the air in that pocket left, actually there is a vacuum created, it gets sucked into the metal stream and mixes with the metal stream. That creates a lot of other hassles, more turbulence, oxidation of the metal, air aspiration, gas porosity, all those things. So flow should not separate from the mold walls, or at least the gating channels. This is one fundamental lesson from here. Okay, now what happens after the section is passing by? If you look at the V2 equation, okay, we said V2 is equal to cross section area is there, but we cannot just say it is equal to root over 2GH. There will be some losses taking place, okay, and we will look at losses shortly in the next slide. And there are various ways to look at estimate the losses for different kinds of cross sections. So the loss factor is called as discharge coefficient or CD, and there is a little complicated equation for CD calculation in terms of CD is 1 by root over 1 plus sigma or sum of different what's called as K's, okay, because the flow may go through several types of, a bend will be there, a junction will be there, a expansion, a contraction. So you have K's values for all those things, and if you take sigma K and then 1 by 1 plus sigma K, that gives you the discharge coefficient, okay. And in a way the K also is related to the cross section changes, A1 to A2 change. No need to worry about this, but let us look at the different kinds of cross sections here, changes here. So if you have sharp entrance, K is 0.5. Remember this K can be, it's not the loss factor. You have to actually map the K into the finally CD, which is the loss factor, alright. So you have rounded entrance, sharp bend, rounded bend, okay. Then you have sudden enlargement, you may have sudden gradual enlargement, okay, and sudden contraction and a T junction. So take the K values from this, map it back to CD, and you have some reasonable value. Okay, hey, I don't have that much time to do all those things, fine. In metal casting, typically you can take values of CD as about 0.6 to 0.8. You're not doing too wrong. But then 20% change is a lot, so if you are really finicky about it, you can use this equation to find exactly how much loss is taking place. This is for flow through the gating channels. Okay. Now we come to another interesting observation. You must have seen that if you are gardening, okay, and you are trying to water the plants, and let's say you are very lazy and you want to stand in this place only and you want to water something which is very far, you put a finger on the pipe, and you put a little finger and then it goes a little farther. You put little more finger, it goes that much distance, then you want to water the wall there, and you put really finger almost on 99%, and then you find it doesn't go there, in fact it comes back. The flow rate actually, as velocity actually comes down. So what is going on here? If I go back to my original equation saying A1 V1 is equal to A2 V2, I am reducing the area, so velocity should increase, but it doesn't follow that rule either. Are you getting? Okay. Did you do any gardening, all of you? All right. Can you imagine what is happening, right? I mean, you try to reduce area and think it will go higher velocity, but it doesn't really go after some time. It goes first few attempts, but then you increase it more, it doesn't go. Okay. So what is happening here is this. Let us go back to our head of 20 centimeters. Okay. And there are two factors coming into picture here. One is the A1 V1 A2 V2 continuity equation, but second one is a discharge coefficient which also is changing. As you are covering more and more area, your discharge coefficient value is coming down. Okay. So initially if you see, my velocity increases from 1.6 to 1.8 meter per second, okay, but as I cover more area, my flow losses are increasing so much, my velocity starts coming down again. Okay. And so if you look at the discharge of course keep coming down all the time because I am covering more and more area. Is this clear? Okay. So you can learn a lot of metal casting from gardening. That's the lesson here. Now we will go into one more concept, which is choke. Okay. They say choke, and choke is nothing but the smallest cross section area in any piping system which controls the flow rate. So if you want to control the flow rate in your wash basin, you are using the tap. Essentially what you are doing is we are changing the cross section of the flow. We are not changing anything else. The tank height is same, pipe diameter is same, everything is same. Only changing is the cross section area of the tap. By doing that, I can control how much time it takes to fill up a bucket of water, let's say. Okay, that's the same concept here, except that you please remember that you have two factors coming into picture. One is your area coming into picture, second is your discharge coefficient coming into picture. So losses and the cross section area. So we'll use this knowledge to our benefit when we are controlling the flow in a gating system. Now people say or talk about friction losses. Okay, and all of us have studied, at least in engineering, most of us, you have this pipe, long pipes, and civil engineering people talk about losses in a friction losses in a pipe and so on. What I want to tell you here is that when you're talking about pipe loss, it is applicable only when talking about long pipes going into hundreds of meters and kilometers. Here talking about just maybe a few centimeters, maybe a meter at the most. So their friction losses really doesn't come into picture. So you can safely ignore friction losses in metal casting. Okay, we only worry about the losses of contraction, expansion, and so on. Then we have an issue of my flow is no longer through one channel nicely only like civil engineering. The pipe is now splitting into multiple channels. Okay, so each gate or each runner from a sprue is a different opening. Now what is distribution of flow in that? Is it equal in that? Supposing I have a junction like this, okay, and the flow is coming from the left side there, and it's coming out in one T gate, another T gate, and the last gate which looks like a L gate. Will the flow be same in all the gates? Anyone can tell me? Will the flow be same, or will it be more in one of them? Which one will, if it's more? Area, let us say, is same. Let us say area is same. Last will be less. We have to, last will be more. This can be proved only by gardening again. Okay, you take the garden pipe again and make 3 holes and find out. Okay, but it's true. I think he's maybe tried it out himself. So actually, you find the more flow coming out from the last gate, primarily because of inertia. By inertia, flow goes to the last one first, comes out of, then it reverts back and comes to the front gate. So between the 3 gates, if you see, the L gate a flow rate is more than the T gates, because L is always the last gate. You can't have L gate in the middle. When the moment you say L gate, it is the last gate. So L gates will always have more flow rate than the T gates. Now between the different T gates, if your cross section area is changing, that is a function of the gate area, runner area. As a gate area, yeah. Yeah. In a way, you're right, because you have runner extension at the end. So I agree with you, right? Okay. So you never have a, but between different T gates also, you will find that the farther T gate will fill first. That is the point we are trying to make. And then also how much flow rate is taking place, you can estimate from this graph, which is a function of the gate area by runner area. So more the gate area compared to runner area, the more obviously the flow is going to come out of the gate, which is common sense here. But we can use this to actually calculate the discharge coefficient. Yeah. The last gate always. Yeah. Okay. Next concept we'll look at is the velocity at the gate exit, so which is root over 2gh we said. That is only the velocity coming out of the gate. Then it follows again what we call as projectile motion, right? The bomb coming out from the warship. So if you are looking at that, the path of the projectile motion of the well jet, it is possible to actually estimate where it hits, with what velocity it hits, and with what angle it hits. And the equations are here. So if you look at the same example which you have been following up now, that to calculate the distance and angle and all that, we need to first calculate the time of flight, how long it flies. Okay, and time of flight is given by tau. We are going to use the symbol tau for time in this throughout the course. Root over 2h by g, which is about 0.1 second in this case, and the horizontal range nothing but your horizontal velocity into time, which comes to about 20 centimeter in this case, and the vertical component you can calculate by this equation. Once you have these two components, the actual impact velocity is a vector sum of horizontal and vertical component. You don't have to derive these formulas, you can just use the formulas and get the actual impact velocity. Then you can also calculate from that by which is tan inverse of v by v gate. Most calculators, even iPhone now has a scientific calculator, so you can just hit tan inverse and calculate that. So you can actually, now what is more dangerous? You want to impact at 90 degrees is worse, or at 0 degrees is worse? obviously hitting like this is worse because hitting with the full force of the metal. But if you are hitting like this, in fact if you are hitting horizontally, the vertical component is 0 and in fact it is harmless, almost harmless, and in theory it is harmless at least. So whenever you calculate the angle, you can calculate the vertical component and see with what is the effective impact velocity of the metal there. Okay. But that is not enough velocity. Between a aluminum stream and a steel stream, you know which is going to create more damage. So you have to bring in the momentum into picture here, which is mass into velocity. So for the same volumetric flow rate, you can use density as a measure of comparing the impact of the aluminum and steel, right. So in this case, the P is a symbol used for momentum, and so P is equal to rho into velocity of vertical velocity of impact. Okay. In this case, it comes to about 7,000 kg meter per second, and the force of impact we can come to finally 0.28, let us say newtons. Then what is the stress? Now that depends on your stream. Is the stream spreading out or is the stream like laser beam, it is focused? Usually spreads out a little bit, but how much spreads out is something difficult to estimate. But if you can even imagine that the worst case scenario is going to be same area as the gate area, worst case scenario, the whole thing is concentrated, it is not spreading out, same as the gate area, it comes to in this case 1.4 Newton per meter square. And for green sand, you know strength is about 30 to 50 kilonewton per meter square, is it? Okay. Okay. So this is how we can estimate the impact of a stream. So what we have seen in this is that metal flow is a first of all complicated phenomenon, but we can have some simple measures to understand the flow. So we looked at pressure, converting pressure into velocity, velocity into and velocity flow losses through different channels, continuity equation, okay. And from that we looked at the flow through different kinds of gates, first gate and last gate and so on, and finally how the metal, your stream is going to be impacting into the mold cavity, and we can estimate the effective velocity of impact, momentum of impact, angle of impact. From that we can estimate if any mold is going to have a damage there. Okay. So this is quickly about flow.